In this video, we're going to be describing initial conditions and particular solutions. So we're going to be given some information about a graph, and we're actually going to be able to find the antiderivative. And instead of just putting a plus c, that constant of integration, we're actually going to be able to solve for that variable and start to put a number there. So in this example, we're given the derivative function, and then we're told that the antiderivative graph passes through a certain point or touches this point. So the antiderivative of the derivative would be the original function. So we know where the original function is touching or a point on it. So we're going to be able to find the antiderivative of this and then use this information to plug it in and find that value for c. So the initial condition is just telling us some information about the original graph or the antiderivative. An input or an output or a point on the graph is usually given for that initial condition. So let's do our first step. We're going to find the general solution. So we're going to find the antiderivative and add that constant of integration. So if we find the antiderivative of 3x squared minus 1, we're going to use our power rule and then simplify. And so we get the antiderivative as x cubed minus x plus c. We're actually going to be able to solve for c using this initial condition or this 0.24. So we're told that that's a point on our antiderivative graph. So if I plug that into my antiderivative, if I plug 2 in, I know I get 4. Well, let's see what happens. So if I set or substitute 2 in for x and set this equation equal to 4, then we're going to be able to solve for c. So by substituting 2 and solving for c, we get a value of -2. So now I can go back to that general solution, which is the antiderivative or a family of antiderivatives, right? And then we're going to get a particular solution. So based on this condition, we now have a definitive function, x cubed minus x minus 2. We're just plugging that -2 into that c spot. So there's our original function. We could check our work. We could derive that and hopefully get 3x squared minus 1, which is what we started with. So let's do another one. Slightly different wording in our problem, so let's try and figure out what we're given and how we can use it. So we're given the derivative of the antiderivative. So that must be the original function, 1 over x squared, for any values that are positive or greater than 0. We want to be able to find the particular solution that satisfies this initial condition. So this would be a point of our antiderivative. Well, we need our antiderivative. So if I know that my derivative of my antiderivative is 1 over x squared, well, remember, if I integrate a derivative, I just get the original function out of it. So I know that if I integrate or find the antiderivative of this, I should get the antiderivative. Kind of confusing to say. So let's just integrate this. So 1 over x squared I could rewrite as x to the -2. And then I could integrate it using my power rule. And I could get x to the -1 over -1, or just negative x to the -1 power plus that constant of integration. That's the general solution, the family of antiderivatives. So if I want a particular solution, I got to solve for c given an initial condition. Well, we're given the initial condition right up here. Given this coordinate of our antiderivative, I now have my antiderivative equation. So I can just plug 1 in for my input and set my function equal to 0 and solve for c. So we get a value of 1. So now I can take that, plug it back into my general solution to get the particular solution based on this initial condition. So just substituting c for +1, and we now have our particular solution. In this case, we want to make sure and also define x as being a positive value, just like we were told at the beginning. So that's basically it. Figure out how you can use that initial condition to substitute into your antiderivative to find your particular solution based on that condition.